differentiation. Okay, even though I have not give a live session on numerical differentiation, but I think you can watch the video. You can watch the video here. And then we have our mid-semester break, and we have numerical integration, which is supposed to be last week. And this week is again the continuation of numerical integration. Okay, if you look here, for this week topic, numerical integration, Richardson extrapolation and Gauss quadrature, okay, is in this video. Okay, sorry, Richardson extrapolation might not be in this video, but Gauss quadrature is in this video. Okay, Richardson extrapolation is just a one paragraph or one or two paragraph in your textbook. So you can read this on your own, and it's a very straightforward, simple and straightforward. And Richardson extrapolation appears in both integration and differentiation. Okay, so this is just a matter of extrapolation. So please watch the video on this numerical integration. We have Newton Cotes quadrature, and of course, we also have Gauss quadrature explanation in that video. Okay, in that video. Maybe I need to change this and put Gauss quadrature. So you can watch this video for these 2 weeks. 2 weeks punya planning, numerical integration for this and integration for this. So it's all in one video. And I'll give you an assignment later tonight. Later maybe tonight or tomorrow. For this numerical integration topic. All right, so again, I keep reminding you about project. So please find a group, group member. So our project will be a group of 2. So again, when you choose a member, make sure you choose the right member. Janganlah pilih orang yang tak pernah buat tugasan, yang hadir hujan tapi tak submit satu pun soalan. Okay, this is not a good team member. So please find the one that yang akan bekerjasama lah, yang akan bekerjasama dengan kamu. Alright, so hopefully you have already in mind your team members. Lepas ni saya akan minta lah senarai nama group tu. I will ask for your names of the name of your team members supaya saya boleh keep track lah. Alright, so what I'm going to do today is to start the lecture with numerical integration. Numerical integration. So okay, so I think I can stop sharing this e-learning portal. By the way, please visit this e-learning portal. Okay, so let's share this. Let's stop sharing this website. Okay, so I need to save all the memories. Okay, so okay, let's start with the lecture with numerical integration. Numerical integration. So let's start with something simple first. Okay, something simple. I think you done this a lot of times, even from your high school. Tingkatan 4, tingkatan 5, your form 4 and form 5, you have been using integration and differentiation a lot. You have been using integration and differentiation a lot. So let's talk about what is integration and what is just what is integration, because we are not covering other than integration this morning. This morning. Okay, so let's share my piece of paper here. Okay, this one. Okay, so this is the one. This is my piece of paper, and let's talk about integration. So I think everyone here is very familiar because I think you've seen this before, right? So integration is just I equal to, okay, from A, lower limit of A, B, fx, dx. Okay, so this is the integration, right? This is just the integration equation. Okay, you've seen this a lot. This is the analytical methods of doing the integration. So how do we make this numerical? How do we make this numerical? Right, so let's look at this. So before that, let's try to understand what are these. So this is what we call the lower limit and the upper limits of the integration. Okay, and fx is a function. Okay, it's the function that we want to integrate, or commonly known as integrand. Not integrate, integrand, integrand. Okay, and a and b are limits of integration. So if fx is continuous, finite, and well-behaved, then we can evaluate it analytically, which means that if, let's say, this is my function, and this is my lower limit a, and it is my lower limit b, if that function is continuous, okay, so this is continuous, from a to b is continuous, finite, we can see the value for each of these value for each of the points in this curve, and well behaved, this is very smooth, then we can say it can be evaluated analytically. Okay, so what do you understand about integration here? What do you understand about integration? You did this a lot, right? So basically, what is the physical meaning of integration? Can anybody tell me? Can anyone tell me? Are you there? Or are you just logged in and not in front of the screen?
Yes, sir. Yes.
Okay. Okay, say something.
Integration means that we find the area under the curve for the function fx. This is my understanding.
Okay, so basically it is just trying to find the area under the curve, right? So based on that, we can formulate a numerical method. Okay, based on our understanding of what is integration. So this is the first step. Okay, this is the first step. So remember, my teaching philosophy is always for you to understand. That's the first thing. Okay, because just like an example, I can give you yesterday, I have this finite element class. One student was asking me, okay, last semester, the same thing last semester, my master student was asking me, after I returned the test papers, they say, sir, can we see the solution? Can you share the solution? You know why they are looking for the solution? Saya baru post benda tu. Saya baru post dalam group. Saya kata, okay, your graded papers is on e-learning. After less than 15 minutes, somebody dah minta dah. 2-3 orang minta. So they are trying to, most of them are trying to memorize the steps. Memorize. Again, if you remember during the earlier this semester, I told that memorization is the lowest step of understanding, which is your Bloom level, Bloom taxonomy level 1, kan? So we do not want that. So we want you to understand. So this is the idea. So now you understand that integration is basically just trying to find the area under the curve, right? That's it. You are trying to find this area. Okay, so we know to do this mathematically, you have to integrate this. So basically, I is area under the curve. Okay, so how do we do it numerically? Okay, how do we do it numerically? That's the idea here. Okay, so we need to find the area under the curve. So what do we do? The simplest way is to just use your graph paper, right? Just like this one here. I have already boxes, yeah? Okay, so this is maybe 5 millimeter square, 5 millimeter square. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So we know. So this is how we approximate. Remember when we did for root finding? The first thing that we do was, okay, let's plot the graph and see where does the line intersect the x-axis, right? So that's how we do it. So once we know, then what we do was we improve the approximation by, okay, let's say we try using the bracketing method. Okay, we say, oh, bracketing method is too slow. Okay, why not we try with open method? either Newton-Raphson method. Okay, we tried Newton-Raphson, but the equation was too hard to differentiate because we need to find the gradient, right? We need to find the gradient. So we need to find the dy dx, the integration, the differentiation of that equation. So might be the integration is just too hard. So we say, oh, okay, this will not work. So why not we try with second method? So second method is quick, right? It's quick, provided that we know there's a root in between, right? So this is how we do it. So the same thing here. So what we are trying to do is we know the definition of this equation is basically area under the curve, right? Area under the curve. So how can we find the area under the curve now? Okay, that's the target here. That's the target here. All right, so how do we do it now? How do we do it? Okay, so there's a lot of ways to do this, right? So let's say we are trying to find this area under the curve. Okay, so let's do this. Okay, so maybe what I can do here. So let's redraw this this curve. So this is our limit A, lower limit A, and maybe this is our lower limit, upper limit B. So if you look at the squares in my screen here, so it's about 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. It's about here, it's about 16, 17, 18, 19, 20, 21. About 21 squares, yeah? 21 squares there. So that's one way of doing it. So can we also, oh, before that, let's try to define what is, okay, oh, before that, never mind. Let's try to calculate. Can I do this? Can I find my area using can I find the area? Okay, can I approximate the area using this? Oops. Okay, so this is the curve. Can I use this area? So can I use this area here? Okay, can I use this one? So this is basically just this is our f, okay, equation. This is x. It's our fx. So this is the value. Maybe this is f at a time. Okay. So the formula for area is just, in this case, this height times this base times b tolak a, b minus a. So what's the issue there? What's the issue there? What's the issue? Is this a good approximation? No, this is not a good approximation. It is an approximation, right? But this is way too much error. Why? Because I underestimate. What about this blank area here? What about this blank area? I didn't calculate that one. So this is the sources. This is one of the sources of my error. Okay, so let's try doing the same thing now, but let's do the same thing again, but let's do this. Okay, again, the same thing, the same curve. Of course, my handwriting is not good enough. Okay, A and B. But now, instead of using only one intervals, I use one more interval. So let's say this is C in between. So can I calculate the area using this area plus this area? So now the area is basically, the first interval is FA, which is, this is FA, right? This is FA times C minus A plus this one, which is now FC, and then B minus C. So in this case, what we can say is that the integration is this, okay, for the first case, and for the second case is this. So which one do you think is better now?
Second one.
Second one. Why? We can see that I underestimate less error here, right? Because the one not shaded area here is lesser than this. So can you see that if I have more intervals, it becomes better? Okay, so this is one way. So instead of having only one interval, why not have a lot more intervals? Okay, as the thing gets smaller, the more accurate the result will come to, right? This is the idea, right? Again, numeric method is all about this. First, we approximate. We know that there's a lot of error. Then we try to improve by making it lesser error. So this is one way of doing it. And you can see that if I have more and more interval, the error becomes lesser and lesser. For example, if I have, if I do this, let's say if I split this, so now I have 1, 2, 3, 4 intervals. What do you think will happen? The error become much lesser, right? Because now we can approximate this, and then we can approximate this. So now you can see that the unshaded area become lesser, thus the error become lesser, which makes our approximation become better. So this is the idea. And this is the definition of integration. So integration in mathematical sense is basically just I equal to the summation of f, which is the function or the height of fi times the here is what we call the interval. Let me denote that as h. So this is our interval. Our interval b minus a is h. So this is our h time h. Okay, and as h approaches 0, this becomes integration of b a f x dx. So this is the definition of integration. So basically the area under the curve. So we started the other way around. We started by understanding the definition. We know that we are trying to find the area under the curve, and we try to formulate. We try to see how can we make it better and better. So this is what we call, by the way, because we are trying to find the rectangular area. So this is what we call the rectangle rule. Okay, because we use rectangle to find the area under the curve. Okay, so what are the issues? Can we improve on our rectangular rule here? What else can we do other than increasing the number of intervals? What else can we do here? Any idea? Okay, let's see if we can do this. Let's see if we can do this. Now, okay, let's say, okay, we have a curve here. So let's just assume let's assume just one interval, because we know if we have more interval, then the approximation become better and better, right? So let's say this is my curve, and this is the interval. Okay, this is one interval. So I think in our first approach, what we did was we are trying to use this. Okay, we use this point here as the height of the rectangle. Okay, so the problem there here is underestimate. Okay, underestimate because there's a lot of errors here. So what if we use this one now? Okay, second approach, same curve. Okay, same curve, but now instead of using this point, I use this point here. So my rectangle will become this. And what's the problem with this thing here? This is overestimate. Overestimate. Overestimate because we calculate the area we are not supposed to calculate, which is in this case this part here. Okay, this is one of the sources of the error. Again, is more. What if we do one more time? Let's redraw this and do it this way. Okay, so this is the interval. Okay, now instead of taking this point here or this point here, I'll take the middle point. This is the middle point, this point here. So I'm using this point as my height of the rectangle. So which one do you think is better now? Which one do you think is better? The first one, the second one, or the third one? Senyap macam ni. Ada orang, tak ada orang ni?
Third one?
Definitely the third one. Why? Why? If you just look at the drawing here, you can see that, okay, I underestimate this part, right? But at the same time, I overestimate this part. Hopefully, this error and this error cancel out. So this is a much better approximation. What I did was, I'm taking the midpoint instead of the first point or the left point or the right point, but I am taking the middle point here, the middle point. So this is what we call, where is it here? Let's see, I'm looking for my notes here. Sorry, I'm looking for my notes. We have what this is. Okay, so in this case, this is what we call the left, left sum, because if we have more interval, then we are summing based on the left point. So this is what we call left sum, and this one is what we call the, let's say we have more interval here, so this is what we call as the right sum. Right sum. Okay, so, and of course the last one is what we call the midpoint, what we call the midpoint sum. Okay, midpoint. As you can see that in this case, midpoint sum has a much better estimate than the other two. So in this case, in the rectangle rule, we have three kind of results here. So we have left sum, we have right sum, and we have the third one as the midpoint sum. Okay, so we improve, right? We improve the method now. So other than having more intervals, so taking the height of the function is also important. So in this case, instead of taking the left point or the right point, we take the midpoint, which we can see that it has a better estimate than the other two. Okay, so we done this. So what else can we improve here? What else can we improve here? Ada lagi cara tak? Any other way that we can improve this? Okay, so we have done two steps. I mean, two approaches to making our estimation more accurate. One is using more intervals instead only one interval. Okay. Second is using midpoint instead of left or right point. And what else can we do here? What else can we do? What else can we do here? What else? Anything? So this is the way to go for rectangle rule, right? So let's do this. If we look at the left sum, integration of from b a to b of fx dx is just approximately h, okay, summation of all the intervals, okay, from fi times fi, right, I equal to 1, sorry, from, in this case, if this is f0, okay, f0, this is f0, f1, and f2. So from I equal to 0 until n minus 1, n minus 1. Okay, so this is for our left sum, left sum. So for our right sum, I is equal to approximately h is the interval, I equal to 1 until n of f, or we can do it this way. We use the same numbers, but this is from fi plus 1, which is our right sum. And for midpoint, then we have h, summation of I equal to 0 until n minus 1, fi plus 1 divided by 2 times h. Okay, so this is our midpoint sum. Okay, so what are other ways that we can do to improve this? Any other ways? Any other ways? Okay, I hope you can see. This is always the approach of numerical method. We approximate and make it better. We approximate and make it better. So, there any other ways to do this? Any other ways to do this? To find the area under the curve? Any other method? Okay, so take note that in our rectangular rule, we use a straight line here, right? Straight line, straight line, straight line, straight line, not a straight line, horizontal line, to be exact. This is horizontal line, and this is another horizontal line. My PC is acting up. Okay, so horizontal line and horizontal line, right? So horizontal line. Okay, let's keep that into mind. Let's keep that in your mind that we are using rectangular rule is using a horizontal line. Okay, so let's look at again this point here, this curve here, and okay, let me make it more curvy here so you can see. Okay, something like this. Okay, so let's say, this is not good enough lah. Let's change that. Okay, let's do it maybe slightly this one. Okay. So this is our A and this is our B. Okay, so what we did was just now is that this is our fx, right? This is our function fx. So what we did just now, we approximate fx, okay? We approximate as polynomial of the zeroth order of x. So what is a polynomial of zeroth order? So note, polynomial is something like this. Pn is a0 plus a1 x plus a2 x squared plus a3 x cubed plus and so on. This is just like your regression last time that we did, right? Regression last time. So we are using quadratic or linear regression, right? So in this case, fx equal to p naught x means it is a zeroth order, which is just a naught. So what is a naught here? What is a naught? If you look at this polynomial, a naught plus a1x, a naught is a constant. A1 is a function of x. It has this is linear order, right? Because this is just like your y equal to mx plus c, right? So a naught. So this is a constant. And this is the basis of our rectangular rule because we can take our a naught as this. We approximate this function as a constant, okay? As a constant. Note that this is fx. This is second order. Definitely this is at least second order because it has a curve here. It has a curve here. Right? It's not a straight line. It is a curve. So we can take a naught at this point, or we can take it at this point, or we can take at this point. Maybe we take this one and this point. So this is the definition of we approximate our function fx as a polynomial. This is of the zeroth order. Zeroth order means just a constant. So what if we approximate? What if we approximate our polynomial, our fx now using a first order, which is now a naught plus a1 x. So this is what I call a linear line. So what is this? Look at this. This is similar to your y equal to mx plus c, which means it has a constant with a line that has a slope. So what if we approximate our area now using this? This is the line. So this is our P1 x, which is a naught plus a1 x, our first order polynomial. So look at this. Do you think this is a better approximation than using rectangular rule? What do you think? It is better than midpoint? Okay, let's look at this one. Let's look at this one. So we did this before, right? So now, this is only for one interval. So what if we have a lot of intervals here? Okay, now for this interval, I'm using a linear line, which is this red color here. Okay, let's zoom in. And let's zoom in here. So do you think which one is much better here? Do you think the midpoint is much better, or do you think the linear line is much better? This has this small error here, right? And this small error here. Okay, so what do you think? Which one has the better approximation?
Midpoint.
Midpoint. Okay, so I'll give you an assignment on that to prove that what you are saying is correct. Okay, so I'll give you the same curve and you try to do it using midpoint and your linear line. See what's the result? Which one is much better? Okay, so I'll give you an assignment for that. Okay, so this is what we call, because if you look at this, okay, of course, if you have more areas, if you have more and more intervals, the error becomes lesser and lesser, right? So the first step is always to have more intervals. More interval, of course, will reduce the error. So we prove that with our rectangular rule. So we say, okay, why not use more intervals? Okay, so we'll lessen the error because by definition, you can see that by definition, where is my definition? Yeah, by definition, as h getting smaller, the result become better. Okay, the result become better, except for this one, yeah, how we approximate this, yeah. So we prove that more interval h becomes smaller, then we improve. And the other approach that we can do here is we improve our approximation of f. Yeah. So we did say we try with f of a naught, which is our rectangular rule, and we try with a naught plus a1 x. Okay, a1 x. So which is this one. So linear. So if let's take a look at this. Let's say I have 3 intervals for this one. Let's say I have 3 intervals for this one. Now what I can see is that if I'm using my P1, my linear line, the area become this. Okay, so this will be the area, and the error is just this small part here, small unshaded. So this is the one. Okay, so this. Okay, let's look at only one interval now. Let's look at one interval. Okay, this is only one interval. So how do we calculate the area of this interval here? Can anybody tell me? So let's say this is f0, f1. Okay, so how do we calculate this one? And of course, the let's say this is I equal to 0, f0. This is I equal to 1. So what's the area here? Area equal to, this is h. Okay, the area is the area is f1 plus, sorry, f0 plus f1 divided by 2, or let's do it this way. Okay, half of the height times h. Okay, so this is the average height between f0 and f1, the average height. F1 f0 plus f1, or this is simply h over 2 f0 plus f1. And if you recall from your math classes during high school, this is what we call the area of a trapezoid. So this is trapezoid, trapezoid. So now this is what we call when we use this, then, okay, this is what we call just now rectangular rule. And in rectangular rule, we have 3 methods. Left sum, right sum, and midpoint sum. And this one is what we call the trapezoidal rule. trapezoidal rule. Okay, so now we have one more approach that we can use to improve the accuracy or the estimates of our area under the curve. So one is, of course, increase the number of interval in such way that our interval size become, I mean not size, the width become smaller, and then the second one is this, approximate the fi or the function, approximate the function. So this is what we call the linear. So rectangular rule, the rule is very simple. It is just f times h. Trapezoidal rule is half of f0 plus, sorry, fi plus fi plus 1 times h. This one may be fi or fi plus 1. Okay, this has 3 rules. So this has 3 methods. So either fi times h, fi plus 1 times h, or fi over 2 times h. So left rule, right rule, midpoint rule. Okay, I over 2 means half of the width. Okay, so this is the way to do it. This is the way to do it. Okay, now, so for this case, what's the area here? So what's the area here? So let's use trapezoidal rule. So let's say this is our f0, f1, f2, and f3. So what we can do here is for the first interval, the area is just f0 plus f1 over 2 times h, okay, plus f1 plus f2 over 2 times h for the second interval, and for the third interval, it is just f2 plus f3 over 2 times h. Now we can take out h over 2, okay? So the area under the curve in this case is just equal to h over 2, h over 2, f1, f0 plus f1 plus f1 plus f2 plus f2 plus f3. Okay, or this is just h2 f0 plus 2f1 plus 2f2 plus f3. Okay, so this is the area under the curve for this problem using trapezoidal rule. You can do the same thing for rectangular rule. You can also use the same thing for your rectangular rule. For example, for this one, this is just f0 times h plus f1 times h. So h f0 plus f1. The same thing with this one, the right sum, this is just f1 plus f2 times h. Okay, the midpoint is, again, you have to take the middle point, right? You have to take the middle point. So in this case, h of f1, f0 plus f1 over 2 plus f1 plus f2 over 2. So of course you can simplify this, right? You can simplify this, or in this case, this is just f0 over 2 plus f1 plus f2 over 2. All right, so the same thing here. So now, any other way we can improve this? Okay, there are only 2 ways, right? There are only 2 ways. We done this. We done this. Okay, so the next thing to do is we try with zeroth order, which is just a constant, and become a rectangular rule. We use with the first order, which is a linear line. Then we got what we call the trapezoidal rule. And what if we improve our Fi with the second order. So can we try with now Fx instead of P naught polynomial of the zeros order or the first order? Now let's try with this second order, which is A naught plus A1 x plus A2 x squared. So now this is a quadratic. This is a quadratic. So note there are three unknowns, right? There are three unknowns. 1, 2, 3. A0, A1, and A2. There are three unknowns, which means how many points do we need to use this quadratic approximation? For linear, we have A0 and A1, two unknowns. How many points do we have? We have 2 points. This is the first point, and this is the second point. That's fine. So we have two unknowns, 2 points. We can solve the equation. But in this case, we have A0, A1, and A2. We have three unknowns. And in this case, if we have only one interval, so we have only 2 points. So this rule, this approximation, cannot be used for only one interval. It needs to have 2 intervals. Okay? For example, let's draw this again. Okay, let's draw this again. Okay, time is running out. Okay, so this is the curve here. This is the curve. So this is my A and my B. So the minimum number to use this point, to use this quadratic approximation, is to have 2 intervals, because this is already 1 point. This is another point. So we need one more, right? We need one more. So we can have somewhere in the middle here. Okay, so this is H, this is H. So now we can use this, and note that for our linear line, linear approximation, this is a straight line, right? This is a straight line. This is a straight line. But now, let me change to red color so you can see. So now, when we use this, when we use this equation, this and
Doktor line, Doktor.
Should be
Tak clear, Doktor.
some
Doctor, I think you have a problem with your internet connection, Doctor.
something like this. Maybe this. Okay, something like this. I don't know how it's fx second or same line. Okay, so in this is sekali A0, A1. Apa dia? Excuse me. Yeah. Dia masalah lagi. So is it okay? Why not? So, let's watch my video. See you next Sunday. Next Sunday. Thank you.
Thank you, Doktor.
All right.
Thank you, Doktor.